In this video, we will examine how angular momentum is conserved even when the inertia of an object changes.
Alright, to explain what happened in the video of Nathan when he pulled his arms in while he was spinning, we're going to use the angular momentum lens. We're using this lens because angular momentum is conserved because there are no outside torques. So L initial equals L final. And since angular momentum is the moment of inertia times omega, we conserve momentum. And momentum is a vector, and so is angular velocity. So I initial and omega initial are going to equal I final times omega final.
We are estimating Nathan's mass to be 70 kilograms and the mass of the water bottles to be 4 kilograms each. We measured Nathan's disc radius to be 0.25 meters and the water bottle's radius to be 1 meter at extension.
So initially, it's just Nathan, so his moment of inertia is right here, and we're treating Nathan like a solid disc. So we add the 1/2, and we have initial angular velocity. Now when Nathan pulls his arms out, now we have to take into account the 2 water bottles, and we're treating the water bottles on the outside like a hoop. So we have this, and then we times it by 2 because there's 2 water bottles, and then there's the final angular velocity. Parallel axis theorem, the water bottle is moving in a circular path, but it itself is also rotating. However, the water bottles are only 6 centimeters, so we're saying that its moment of inertia is negligible.
After simplifying the equation, we found that the final angular velocity should be about 1/5 of the initial.
According to the timer in the first video, the first revolution took about 1.2 seconds. After extending his arms, it took Nathan 4.5 seconds to complete his first revolution.
So taking the revolutions per second from the previous video, we're going to convert them to radians per second. So initially he had 5.3 radians per second, and after he extended his arms, he has 1.4 radians per second. So according to our theoretical calculations, it should be a ratio of 1 to 5, and as you can see, it's pretty close. So now we're going to look through an energy lens. Energy is always conserved, but rotational kinetic energy is not. So hypothetically, if Nathan were to pull his arms back in, that would require work. So these are the calculations, and it ends up that Nathan would require 20.7 joules of work to pull his arms back in. And because he does this work over 1 meter, it's 20.7 newtons of force that requires, and that's equivalent to holding up a 2 kilogram object.